Sarah says that we have a large group today, which is great. So I'm just going to dive right in here. Big picture, the South Saskatchewan River project includes two dams, Gardner Dam on the South Saskatchewan River and the Qu'Appelle Dam, named after the Qu'Appelle River Valley. Together, the two dams create Lake Diefenbaker. Some interesting facts of note about the South Saskatchewan River project are listed on this slide. Gardner Dam is the largest earth-filled dam in Canada and the sixth largest earth-filled dam in the world. Gardner Dam stands 64 meters high, 5 kilometers long, has a base width of 1.6 kilometers, and includes a structure volume of 65 million cubic meters. The Qu'Appelle Dam, by comparison, is 27 meters in height, 3.3 kilometers long, has a base width of 580 meters, and a structure volume of 10 million cubic meters. The Gardner Dam spillway has a capacity at FSL of 6,400 cubic meters per second and is controlled by 11 gates. The spillway itself is 1,170 meters in length. Together, the two dams impound 9.4 million decameters of water, making Lake Diefenbaker the largest water body in southern Saskatchewan at 225 kilometers in length with 800 kilometers of shoreline. Prior to the construction of the two dams, less than 1% of the water that flowed through the South Saskatchewan River was utilized in Saskatchewan. Among the many benefits that Lake Diefenbaker supplies to Saskatchewan are a drinking water source for close to one-half of the province's population, 186 megawatts of electrical generation capacity, and the water supply to irrigate 125,000 acres. Captain John Palliser led the British North American exploring expedition from 1857 to 1861 that explored Western Canada. Captain Palliser's subsequent report to the British Parliament noted the unsuitability of portions of Western Canada for agriculture, later dubbed Palliser's Triangle. The report also noted the possibility of erecting a dam across the South Saskatchewan River Valley to divert water into the Qu'Appelle River in order to create a navigable channel from lower Lake Winnipeg to the Rocky Mountains. The construction of the Canadian Pacific Railway from 1881 to 1885 eliminated the need for a navigable water passage. Communities like Regina and Moose Jaw increased in size in the early 1900s with the completion of the Canadian Pacific Railway. Moose Jaw increased from 1,500 people to 14,000 people. Similarly, Regina grew from 2,300 people to 30,000 people. With this population growth came the need for a secure water supply. The first studies on the construction of the dams on the rivers took place in the early 1900s. The Prairie provinces experienced a severe drought from 1929 to 1937, prompting the federal government to create the Prairie Farm Rehabilitation Administration, also known as PFRA, to promote soil and water conservation. PFRA conducted the test drilling in 1944 to evaluate 10 sites along a 160-kilometer stretch of the South Saskatchewan River to find a site suitable for the construction of a dam. The 1952 Royal Commission findings were not favorable for the development of a dam on the South Saskatchewan River, but the province of Saskatchewan's premier at the time, Tommy Douglas, was convinced that the project was in the province's best interest. Another project proponent was John Diefenbaker. John Diefenbaker became Prime Minister of Canada in 1957. A federal-provincial agreement quickly followed in 1958. The agreement of 1958 detailed that the federal government, through the PFRA, would construct the South Saskatchewan River project, with the province of Saskatchewan contributing 25% of the cost, up to $25 million. The final project cost was $120 million. Furthermore, the province of Saskatchewan agreed to plan, finance, and develop irrigation, hydroelectric power, and recreation facilities. Construction of the South Saskatchewan River project commenced in 1959 and was completed in 1967. SaskPower constructed Cotto Creek Power Station from 1966 to 1969 at a cost of $40 million, with a generating capacity of 186 megawatts. Construction on the M1 Canal was initiated in 1966 and completed in 1967. Ownership of the South Saskatchewan River Project was transferred from the federal government to the province of Saskatchewan in 1969, although the PFRA continued to operate the project until 1997. The project is currently owned and operated by the Water Security Agency. The South Saskatchewan River Project created a true multi-use reservoir that provides a secure water source for municipal, industrial, agricultural, and recreational uses, in addition to providing flood control for communities downstream. A multi-use reservoir feeds a multi-use canal, the M1 Canal. It is a little known fact that the M1 Canal is the first leg of the Saskatoon Southeast Water Supply Canal, also called the Seuss Canal. The two canals together are a vital water source for the province of Saskatchewan and serve 6 reservoirs, namely Broderick, Brightwater, Blackstrap, Bradwell, Zelma, and Delwood. 3 potash mines access their water from the aforementioned reservoirs, and they are PCS Allen, Mosaic Colonze, and PCS Lanigan. BHP Jansen's future potash mine will also be a user of water from the Zelma reservoir. Other users are domestic users, towns, regional water lines, waterfowl projects, 1 provincial park, Blackstrap, as well as 30,000 acres of irrigation in the South Saskatchewan River Irrigation District, and 18,000 acres of irrigation off of the Seuss Canal system. The M1 Canal is 22.5 kilometers in length, originating on the northeast embankment of Lake Diefenbaker and terminating at Broderick Reservoir. Originally, engineers looked at both gravity outlets in the main dam and pump delivery systems. The gravity outlet was abandoned due to design and construction problems. Therefore, all water for these multi-use canals would be pumped from Lake Diefenbaker. The M1 Canal is supplied water by the Eastside Pump Station. The pump station lifts the water out of Lake Diefenbaker and into the M1 Canal. A typical operating season for the canal is May 1st to October 1st. During the years that rehabilitation work on the M1 Canal is occurring, the pump station must be turned off earlier to allow for the construction work. The Eastside Pump Station facility was constructed in the mid-1960s in advance of the M1 Canal. Initially built with 2 pumps, a 3rd pump was installed in 1977 and a 4th pump was installed in 1987. The pumps are supplied through a common intake structure in the lake. Each pump discharges through individual concrete pipelines to a common structure at the head end of the canal. The pumps have a combined design pumping capacity of approximately 23.5 cubic meters per second and a power output of 6,350 horsepower. The Eastside Pump Station has received some upgrades in the recent past that include full overhaul of 3 pump motors, new switchgear, installation of PLC and HMIs to allow for remote starting and stopping of the pumps, and replacement of ceiling fans. On October 1st of 2013, the Eastside Pump Station and its electrical substation were transferred from the Ministry of Agriculture to the Water Security Agency. In the past 50 years, the M1 Canal has been administered by various provincial entities, including SaskWater, Ministry of Agriculture, and most recently, Water Security Agency. In 2008, the Ministry of Agriculture engaged AECOM Canada to create an asset management plan of the M1 Canal. The asset management plan provided a comprehensive assessment of the current conditions of the M1 Canal and its components. The M1 Canal elements were sorted into a priority list of the elements requiring immediate attention without factoring cost into the prioritization. Priority number 1 was given to a highway bridge owned by Saskatchewan Ministry of Highways and Infrastructure, who subsequently added the bridge to their capital replacement list. Priority number 2 was given to cross drains M14, M15, and M124 due to the consequence of failure. Priority number 3 was given to membrane line sections of the M1 Canal. The asset management plan concluded that the existing surface liner, installed in the early 1990s and covering 90% of the length of the canal, had deteriorated to the point that it was incapable of fulfilling its primary purpose of providing seepage control. Furthermore, the asset management plan stated that extensive rehab is required on the majority of the 81 structures found on the M1 Canal. Seen here are just a few of the pictures that I grabbed to show what the condition of the M1 Canal was prior to rehabilitation. A water balance study was undertaken by AECOM in 2010. The Ministry of Agriculture wanted to take the opportunity to address capacity concerns before embarking on a large-scale rehabilitation project with a design lifespan in excess of 50 years. The model that was developed took into account increased irrigation acres. They were estimating approximately 30,000 acres would one day be added. Increased water demand due to climate. A peak daily moisture application of 7.62 millimeters per day was utilized, as this was the highest recorded diversion within the South Saskatchewan River Irrigation District in the previous 20 years. And the model also included increased demand off the Seuss Canal. The water balance study recommended, through previous agreement with the Ministry of Agriculture, that a design flow of 28.16 cubic meters per second, or 994 cubic feet per second, be utilized in the pre-design report. This was a 52% increase in the capacity of the canal. The M1 Canal was originally designed for a capacity of 18.4 cubic meters per second, or 650 cubic feet per second. Aquatic vegetation and seepage complaints were to develop. 30 years after the canal was first constructed, in the late 1990s, a surface liner was installed that covered the majority of the M1 Canal. Due to UV exposure, the surface liner started to break down. The previously mentioned asset management plan stated that surface liners have a typical lifespan of 20 years due to harmful effects of UV rays. The preliminary design report laid out an implementation plan to enlarge the M1 Canal that included design, construction, and commissioning. To prevent seepage, the design included a buried reinforced polyethylene lining system that would be anticipated to have a service life of not less than 50 years. The design elements for the enlarged canal are shown on the screen, as well as the original elements for your comparison. The preliminary design report divided the M1 Canal into 6 contract reaches that were defined by inline control structures. The 6 reaches were further subdivided into smaller contracts that accommodated the Ministry of Agriculture's available funding and allowed for greater budget control through staggered bid closings. And so began the long, windy path to rehabilitation of the M1 Canal, which you will hear in great detail. The picture in the bottom left is the first time that water ran down the M1 Canal in July of 1967, which was about 2 weeks prior to the inauguration of the South Saskatchewan River project. And the picture on the left is a rehabilitated section of the M1 Canal. The pre-design report identified that additional permanent and temporary land control would be required, with the alteration of such canal elements as bottom width, flatter canal bank slopes, increased freeboard, and wider embankments, coupled with upslope tow drainage and excess material embankments. The need for additional space was the first task to rehabilitating the M1 Canal. 38 adjacent parcels would be affected by the enlargement of the M1 Canal. The Ministry of Agriculture, in conjunction with a land agent, secured 91.9 additional acres immediately adjacent to the M1 Canal from 2011 to 2014. As construction progresses, temporary construction easements are secured with the adjacent landowners to provide space for topsoil windrows, haul roads, and material stockpiles. The pre-design report estimated that 163 acres would be required. 6 cross drains were constructed beneath the M1 Canal in 1967 to convey runoff waters traveling through natural ravines and low points from one side of the canal to the other. The cross drains were constructed of corrugated steel pipes ranging in size from 48 inches to 72 inches in diameter. The first construction contract issued by the Ministry of Agriculture addressed the repairs required for the initial 3 out of 6 of the original cross drains. These 3 cross drains were identified as priority number 2 in the asset management plan. Without rehabilitation measures, there was the potential for the cross drains to wash out, which would undermine the canal and cause water outages for an extended period of time. During the winter construction season of 2010-2011, cross drains M14, M15, and M124 were rehabilitated utilizing cured-in-place pipe technology. All 3 cross drains were located in ravines that required large volumes of fill to get from one side to the other. Replacement of the CSP pipes was not the most economical option. Cured-in-place pipe, on the other hand, is a trenchless technology that allowed the deteriorated pipes to be repaired by using a pipe within a pipe application. From the picture on the bottom left, you can see that the original CSP pipes had a few leakage points. The middle picture is a shot of Michaels, Canada. They were the contractor that did the lining, and the picture on the right is the finished product at M124. Ministry of Agriculture released 2 tenders in the summer of 2011 for rehabilitation work in Reach 2. The design was made to leave Reach 1 rehabilitation until last for 2 primary reasons: the high-pressure gas line corridor passing through Reach 1, and the rehabilitation design for Reach 1 contained very little buried liner, as parts of Reach 1 had a clay liner that was original to the canal. The tender pricing was much higher than expected, and the Ministry of Agriculture elected to proceed with only 1 contract. Reach 2C would be the first canal rehabilitation contract spanning 1 kilometer. The pumps at Eastside Pump Station were shut down on September 1st of 2011 to provide some warm, drying weather to the contractor. For the second year of winter construction in 2012-2013, the Ministry of Agriculture requested and received a larger budget of $5 million. The Ministry of Agriculture was able to release 1 contract for 1.74 kilometers of canal rehab. This included the replacement of structures found within Reaches 2A and 2B. The pumps at Eastside Pump Station were shut down on September 15th in an effort to find a compromise with the local landowners. The early shutdown date of the previous year had had a negative impact on the potato harvest in the area. Historically, the M1 Canal would convey water from May 1st to September 30th of a calendar year. The thing that stands out in my memory the most from this second contract is the amount of snow that we had that winter. The contractor spent a great deal of time cleaning out the canal just so that he could get back to work on rehabilitating it. Unfortunately, I can't remember what the Pig's Plain forecast was that year, so I'm not sure if it predicted a lot of snow or not. With the completion of the second year of construction, Reach 2 rehabilitation was complete. On April 1st of 2013, the M1 Canal, Eastside Pump Station, and Broderick Reservoir were transferred from the Ministry of Agriculture to the Water Security Agency. The winter of 2013-2014 would mark the 3rd consecutive rehabilitation construction contract. The tender package included Reach 3A and Major Structures Package Number 1. Major structures involved the retrofitting of 2 check structures, M114 and M121. The addition of automation in addition to adding automation to the check structures. This was the first year that WSA had undertaken the retrofit of a check structure, and we had underestimated the lead time that would be required in getting three-phase power connected to the control building. The rehabilitation work would continue to move north towards Broderick Reservoir. Fiscal year 2015 budget was $9.9 million and enabled WSA to issue 2 concurrent contracts for reaches 3B, 3C, and 4A, 4B, totaling 3.2 kilometers. Reach 3B included the extension of M124 cross drain and the construction of a custom wasteway structure that diverts water in excess of full supply level. I will cover the wasteway in more detail further into the presentation. It was unfortunate that the wasteway structure was not available at the time that this picture was taken. The contractor had to quickly secure 6-inch pumps and mobilize the pumps to site to bring down the water level of the early spring runoff that entered the M1 Canal in March. Fiscal year 2016 budget was again $12.5 million. WSA again issued 2 contracts, one for Reach 4C and a second for Reach 5A and Major Structures Package Number 2. Major Structures Number 2 included the same retrofitting activities as previously described, this time on M128 and M138. This was the first time a contractor was able to dewater a construction reach by cutting a hole in the top of the CSP cross-drain pipe and pulling small trenches in the bed of the canal from either direction to the cross-drain. Fiscal year 2017 budget increased to $12.5 million and enabled Water Security Agency to tender a total of 3.72 kilometers of canal rehabilitation in reaches 5B, 5C, 6A, and 6B.1. Reach 6B.1 was the result of splitting a future design package into 2 packages to maximize budget. Tender pricing had been more competitive than expected. Major Structures Number 3 was also executed in fiscal year 2017 and included M148 check structure retrofits. Fiscal year 2018 construction is currently in progress with 2 contracts to rehabilitate Reach 6B.2, 6C in the first contract, and Reach 6D and Major Structures Number 4 in the second contract. These 2 contracts will complete a combined length of 3.42 kilometers. Major Structures Number 4 includes retrofits to the existing Broderick Inlet structure and the construction of a new check structure immediately upstream of the Broderick Inlet structure. Due to the increased capacity in the M1 Canal, the sidewalls of the spillway into Broderick Reservoir needed to be extended to contain the hydraulic jump produced by the 52% increase in capacity. In addition, a riprap basin was constructed at the end of the spillway to dissipate energy. The radial undershot gate and checkboard guides were removed from the Broderick Inlet structure. The bridge deck was retained, as this is the last canal crossing point for 2 miles. The new check structure currently under construction will be identical to the previous 5 check structures. I will go into greater detail on check structure retrofits on a subsequent slide. With the completion of fiscal year 2018 work, 80% of the M1 Canal will be rehabilitated. The plan for fiscal year 2019 is to initiate rehabilitation work on Reach 1. At this point in time, Reach 1 is currently under design. Throughout the construction, the shutdown for Eastside Pump Station has fluctuated in September. Factors affecting the shutdown date are the weather conditions in a crop year, scope of work for the rehabilitation, and geographically where the contracts are occurring on the M1 Canal. In the course of the rehabilitation, the turnout structures were replaced. Seen here are an original structure and a replacement structure. The conveyance system constructed by the Ministry of Agriculture was designed primarily for flood irrigation. All lateral canals were developed on the west side of the M1 Canal to utilize the natural slope of the topography. Supply pipelines on the west side would evolve later. At the start of the rehabilitation, all turnouts on the east side of the M1 Canal were individual farm diversions to pressurized pivot irrigation. The South Saskatchewan River Irrigation District has been developing pressurized pipelines on the east side of the canal, utilizing federal provincial grant programs. The purpose of drain inlets is to avoid impounding water against the embankment. In the course of the rehabilitation, all of the original CSP drain inlets were replaced as they had reached the limit of their serviceable lifespan. There are two different types of drain inlets on the M1 Canal. Type 1 drain inlets enter the M1 Canal above full supply level. These are ungated, corrugated steel pipes of either 500 millimeter or 750 millimeter diameter. The Type 2 drain inlets enter the M1 Canal below full supply level and include a wet well with a slide gate and high-density polyethylene pipes. Water can be allowed to enter the M1 Canal during the operation season at times when the water level falls low enough in the canal. Originally, all drain inlets were located on the east side of the M1 Canal. The natural topography slopes towards the South Saskatchewan River in the outlook area. As previously stated, there were 6 cross drains constructed beneath the M1 Canal to maintain the natural drainage courses. The cross drains were originally constructed of corrugated steel pipes. The South Saskatchewan River Irrigation District is funding the supply and installation of a 7th cross drain to facilitate the expansion of irrigated acres on the east side of the M1 Canal. The cross drains, rehabilitated with cured-in-place pipe, will require the installation of extensions on either end to facilitate the enlargement of the M1 Canal. The last 3 original cross drains, M135, M142, and M150, were situated in the last half of the M1 Canal and were located much closer to the invert of the canal bed. The final 3 CSP drains were replaced with dual high-density polyethylene pipes of a slightly smaller diameter and longer lengths to accommodate the enlarged M1 Canal. The M1 Canal originally had a wasteway structure located within Reach 3B that allowed the canal to be dewatered into a natural drainage course, whereby the water traveled back to the South Saskatchewan River. The rehabilitation of Reach 3B included a custom structure complete with a 16-inch slide gate utilized for end-of-season dewatering, which is the same as the original structure. In addition, the custom structure also has a weir that would provide an overflow in the event that the M1 Canal should ever exceed the full supply level. Once the water slips over the weir, it is conveyed through a horizontal pipe to a vertical pipe equipped with baffles to lessen the energy of the water before releasing the water back into the coulee. The choice of a weir is due to possible infrastructure failures or large weather events resulting in water levels in the M1 Canal rising above the full supply level. Originally, the check structures had one radial undershot gate and checkboard guides on either side. Both of these measures of control were hand-operated. The retrofitting of the check structures retained the majority of the existing concrete. The center piers were removed and new center piers were cast to create equal distance bays. A sill was also cast to facilitate the mounting of the overshot gates. All of the gates are controlled by rotorque actuators. A stilling well was placed upstream of the check structure and is equipped with an ultrasonic level transducer. The water depth information is relayed back to the control building where all of the automation electronics are contained. Each control building is connected to 3-phase power and they all have baseboard heaters to protect the electronics in the winter. An interesting phenomenon that WSA experienced at one check structure was vibrating gates and fluttering flow. The gate edge was found to not have a sharp enough edge to shed the flow at low conditions. Additional factors that affected the oscillation included surface waves and the gate being free to rotate at its hinge. The solution was to install a sawtooth edge on the gate to better train the flow through defined opening geometry and providing an opening to supply air to adequately vent the nab. The check structure automation hardware includes a PLC, an HMI, an autodialer, and the level transducer. Delco Automation handled the programming for the flow computation through each individual gate using the modified Weir equation provided to them by AECOM. The flow data is logged into the system and can be retrieved at any time. Canal flow data can be utilized to calibrate the Weir coefficient. At this point in time, the M1 canal structures are unable to communicate the collected data back to a central computer. WSA anticipates launching this capability as soon as the last check structure construction is complete. AECOM was just making fun of me this morning that I was going to look like the NASA command center once the data starts coming back in, and I'll have all my monitors surrounded around me. WSA has recently installed a Sontec IQ Plus flow meter in the bed of the M1 canal. At this point in time, there is no flow monitoring on the outlet pipes at Eastside Pump Station. The flow meter was installed at station 0+200 to provide the operations staff with a digital readout of the flow that is updated every 15 minutes. The future plan is to incorporate the flow metering data into the central server in the WSA office to provide further accuracy in determining the quantities of water being diverted from the M1 canal. WSA is working to improve the safety on the M1 canal for the operations staff. Such safety improvements include railings on all structures that require manual operation. Structure identifier signs are provided at every structure to facilitate the timely operation of the canal. In the event of an emergency, these signs will also act like mile marker signs. Check structures are enclosed by chain link fences to notify the public that inline check structures are dangerous to the public. Bollards are erected to notify operations staff and the public of abrupt changes in ground elevations at cross-draining basins. Measures have also been implemented to protect the M1 canal itself and the associated structures. These measures include the overflow structure previously discussed, actuator limits, and generator connections at each check structure. The following measures are used to protect the overshot gates and include the hardwired upper and lower limits that come from factory in the rotork actuators. In addition, there are encoders on the drive shaft that have programmed upper and lower limits that we program into them at the time of commissioning. And then there are slack limit switches and over travel switches located on the cables themselves. In the event that power is lost, a mobile generator can be moved into place to power a check structure. You can kind of see the generator hook up on the side of the building right there. We've actually used this generator for this exact purpose when the utility company's underground power feed to check structure M138 was interrupted for 3 days. So the M1 canal crosses a number of utilities, including a high-pressure gas line corridor, telephone, low-pressure natural gas lines, power, and fiber optic lines. Pictured here is a fiber optic line that was adhered to the side of the bridge deck, and it was encased in a fiberglass conduit. To further complicate the situation, the southern bridge girders had shifted 12 inches on the abutment from their original design position. So you can see here that there's quite a large gap, but the 12 inches that I'm referring to is actually to the west. So this shift placed additional stress on the fiberglass conduit and really didn't provide any flexibility in it anymore. So the outcome The line was successfully relocated beneath the M1 canal by horizontal directional drilling. In my personal experience on the M1 canal, I find that requesting crossings to be relocated is best done 12 to 14 months in advance of the desired results. This actually includes power, new power services to the control buildings as well. So some unique stories on the M1 canal. The bridge inspection reports conducted for the Saskatchewan Association of Rural Municipalities noted some cosmetic repairs were required to concrete surfaces found above grade on bridge M144. During the rehabilitation of Reach 5C, the contractor excavated down to the footings of the piers to tie the liner to the footings as per the design. The piers were noted to have narrowed at the base. Further investigation revealed soft, mushy substance at the base of all of the piers. The two outside piers had been eroded to the point that they were no longer in contact with the footing. Even the rebar had been eroded through. Once the overburden surrounding the piers had been removed, cracks developed in the pier cap. Working together with the local RM, the bridge was closed to traffic. The soft, mushy material was sent to laboratories for testing. The results confirmed the suspected sulfate attack. Based upon the findings at M144 bridge, WSA investigated a second bridge further down the M1 canal that was scheduled for rehabilitation in fiscal year 2018 to determine if sulfate attack would be an issue with this rehabilitation as well. Sulfate attack at the second bridge was noted, but only to a minor degree. This information was incorporated into the following tender package. So WSA conducted a fish salvage on September 29th. A coffer dam at the inlet to Broderick Reservoir was required in order to construct the riprap basin at the end of the spillway. With the DFO letter of advice and the Water Security Agency Aquatic Habitat Protection Permit in place, a Type 3 silt curtain was moved into place in the reservoir, preceding the construction of the coffer dam. The dewatering behind the coffer dam was conducted with WSA biologists in attendance to conduct a fish salvage utilizing a seine net. Approximately 100 fish were salvaged, and many more species were found in the area, some more desirable than others. I am personally not a big fan of leeches. The muskrat was very bold in his attempt to find lunch, and the crayfish were larger than I've ever seen, and they were extremely feisty. It was like a rerun of Fight Club when they were captured in the seine nets together. So to wrap up today, I have included a picture of the M1 canal prior to rehabilitation and a picture of the M1 canal after rehabilitation. That's all I have. Thank you for joining me today. And does anyone have any questions?
Thank you, Kimberly. I don't see, nobody's posted questions yet, but we'll give everybody a moment to put some questions in the question pane if you have any. Yeah, no, thank you very much. Looks like you learned a lot during this during the construction of this.
It's had some interesting moments for sure.
Yeah. Just as a follow-up, everybody will get an email for today's slides as well, and we'll also be posting this on our website under the members only section. Just wanted to remind you of the next Saskatchewan branch series taking place December 12th with Tim Jardine from the U of S, and he'll be discussing the environmental flows for large river deltas. And yeah, if you want to keep getting information for newsletters, just sign up on cwra.org. And if you're not already a member, which I think most people on the call are, but if you're not, by all means, become a member and you get all kinds of discounted rates and conference notifications, workshops, and other online events like this one. Looks like everybody's kind of quiet today, Kimberly. I'm sorry.
That's fine.
But thank you very much again. The City of Barrie would like to thank you and the WSA for your time and contributions. And thank you everybody else for attending today. So thank you very much and have a great day.
Thanks, Sarah.